I'm glad to present our work, D3Fields, Dynamic 3D Descriptor Fields for Zero-Shot Generalizable Rearrangement. In this video, moving a shoe aside requires a dynamic representation for the dynamic motions. Putting shoes on the shelf requires 3D movement. Therefore, a 3D representation is necessary for downstream tasks. Lastly, to align shoes, the representation must encode semantic information, like features for the shoe toe. Therefore, an ideal representation is 3D, semantic, and dynamic. Foundational models have shown zero-shot generalization capabilities. However, these models focus on 2D vision tasks instead of 3D real-world robotic tasks. Consider the task of organizing this table. For the workspace shown here, we have multi-view RGBD observations. We first extract feature volume W from foundation models. For arbitrary 3D points, we project them to image space and interpolate the feature volume W. Finally, we fuse them to obtain the associated feature. We visualize the reconstructed mesh, mask fields, and descriptor fields. Mask fields show clear differences between instances, and descriptor fields show consistent color patterns for object components, like green for shoe heels and red for shoe toes. We also correspond from 2D source image to our 3D workspace, as shown in this example. When the mouse is on the mug handle, all mug handles in the workspace are highlighted. Similarly, when the mouse is on the mug rings, all mug rings are corresponded. For the utensil example, when the mouse is over the fork handle, all handles in the workspace are highlighted, including handles of forks, spoons, and knives. We can also notice that the correspondence is multimodal. When we select the fork head, the heat map highlights two fork heads in the workspace. Moving from the fork head to the knife handle, all handles in the workspace are corresponded again, which demonstrates the consistency of the feature representation. The knife blade in the 3D workspace corresponds with the knife blade in the 2D image. We could observe that the knife handle can be distinguished from the knife blade, even they are visually similar. We rotate and lift shoes and track 3D key points robustly under occlusion. This shows that our representation is dynamic, 3D, and semantic. Given a 2D goal image, we first extract the descriptor map. Then we correspond it with the descriptor field. Given this correspondence, we can compute the MSE loss to define the planning cost. We evaluate our method on diverse objects, as shown on the left, and 2D goal images with different instances and styles, as shown on the right. Here is an example of organizing utensils given the 2D goal image. Even though the goal image has different instances and contexts, our final states still align very well with the goal image. Since our representation encodes semantic information, our framework could win on different instances and goal images with different styles as shown in this grid. This indicates the generalization capabilities of our representation. Our representation also shows generalization across simulation and the real world. In the first example, the goal image is two pairs of shoes in the real world while we manipulate shoes in simulation. The rest of the examples show diverse tasks and goal images, including organizing fruits, mugs, and utensils. Using compositional goal images, the mouse and pen are first organized. Then the mug is placed on the pad, as in the second goal image, using 3D manipulation. Lastly, our dynamic representation enables dynamic manipulation for complex interaction, as shown in the debris collection and shoe pushing examples. More details are presented in our paper.